Welcome to The Explainer. Today, we're diving into something absolutely fascinating, the hidden architecture of decision-making. We're actually going to explore how to mathematically hack human selfishness to build perfectly harmonious systems. Yeah, it sounds crazy, but it's a real field called mechanism design. Basically, it allows us to reverse engineer reality by perfectly aligning our individual selfish incentives with the greater good. Okay, let's dive into this with a classic childhood dilemma. Imagine you've got a single cake to divide between two kids, Mary and Bill. Now, humans, we have these hidden private preferences, right? And we naturally act in our own self-interest. You just want the division to be fair, but Bill, he's going to think Mary's piece is slightly bigger, and Mary will swear Bill got more frosting. The core conflict here is that you, the one cutting the cake, you don't actually have access to their private perceptions. So how on earth do you align their selfish incentives to guarantee they're both perfectly satisfied? Well, the answer lies in a super elegant protocol highlighted by Nobel laureate Eric Moskin. It's called the divide and choose mechanism. The rule is incredibly simple. Really, you have Bill cut the cake, and then you let Mary choose her piece first. That's it. Because Bill knows that Mary is rational and will absolutely grab the larger piece if the split is unequal, his own selfish incentive is suddenly perfectly aligned with cutting that cake exactly in half. He is literally mathematically incentivized to be fair. So, with the cake problem solved, tackling the abstract math behind massive global systems is actually pretty straightforward. Here's our agenda for today. 1. The cake cutting problem. 2. Game theory basics. 3. Enter mechanism design. 4. The VCG mechanism. And 5. Real-world engineering applications. Section 1. The cake cutting problem. Section 2. Game theory basics. To really grasp this, we need to touch on game theory, introduced by John von Neumann back in the 1950s. Game theory lets us model conflicting interactions between rational, intelligent agents who are competing for limited resources. In these systems, everything tends to gravitate toward what we call a Nash equilibrium. So what is that? It's basically a state where a player's strategy is the absolute best response to everyone else's strategies. The problem, though, is that when highly selfish players are fiercely competing, this equilibrium often predicts a totally stagnant, inefficient outcome. I mean, nobody wants to change their strategy because doing so would hurt them, even if a cooperative approach would actually be way better for the group as a whole. Section 3. Enter mechanism design. Now here is where we see a really sharp contrast. Pioneered by the visionary economist Leonard Hurwitz, mechanism design takes those stagnant predictions of game theory and completely flips them on their head. Think about it like this. Game theory is fundamentally about analyzing an existing game. It asks, given these specific rules, how will selfish players behave? Mechanism design, on the other hand, is all about designing the game itself. It allows a centralized entity, what we call a social planner, to start with a desired outcome, like maximizing social welfare, and then reverse engineer the rules of the game to guarantee that outcome. The entire focus here is on perfectly aligning incentives. And this process flows so brilliantly. We start with our agents and their private hidden preferences, just like Mary and Bill with their cake. The social planner takes these potentially conflicting preferences and funnels them through a carefully designed set of mechanism rules right in the center. Because the incentives are perfectly aligned by the mechanism, the output on the other side is this optimized, socially efficient outcome. Section 4. The VCG mechanism. So the really crucial point here is how this mathematical gold standard actually achieves this alignment. The magic trick of the VCG mechanism all comes down to how it calculates payments. It figures out the total social welfare of a system if a specific agent were just completely removed. Then, it subtracts the welfare of everyone else when that agent actually is present. That difference? That's the agent's exact social externality, literally the exact impact they have on everyone else. By charging an agent this precise amount, lying about their preferences becomes mathematically useless. Honesty suddenly becomes their absolute most selfish, dominant strategy. Because of this absolute genius pricing structure, the VCG mechanism guarantees 4 pretty magical properties. First up, truthfulness. Like we said, it's their dominant strategy to just be honest. Second is efficiency. It perfectly maximizes overall social welfare. Third, voluntary participation. This means no agent loses utility by simply agreeing to play. And finally, it's weekly budget balanced, which basically just means the centralized mechanism won't ever run at a financial loss while facilitating all this system-wide harmony. Now let's see how this builds into even broader applications. VCG sits right alongside other frameworks, like the AGV mechanism, which is named after Arrow, d'Aspremont, and Girard-Verret. While VCG is weakly budget balanced, AGV achieves a strict budget balance, meaning all transactions between agents and the planner equal exactly zero. AGV manages to pull this off by relying on agents' prior beliefs about each other using what's called a Bayesian-Nash equilibrium.
Section 5. Real-world engineering applications.
All right, let's shift gears from abstract microeconomics to the physical world, because mechanism design operates in the wild all around us. We're essentially swapping out selfish kids for autonomous network nodes and power grid consumers. In communication networks, the resource is bandwidth, and the goal is maximizing flow without congestion. Down in power grids, the resource is electricity, and the mechanism optimizes demand. Over in security systems, the resource is defensive investment, aiming to prevent vulnerabilities. But in all these cases, the core issue is exactly the same. Agents have private information, and we absolutely have to align their incentives. Let's dive a little deeper into communication networks for a second. Imagine a network manager trying to allocate bandwidth to thousands of competing, totally selfish devices. Instead of forcing these devices to upload massive amounts of private data about their utility, engineers use something called the Kelly mechanism. This brilliantly uses simple, scalar parameterized pricing, essentially just one-dimensional price messages. It literally forces the devices to reveal their true needs through their bids, avoiding massive data bottlenecks while still achieving optimal routing. It's so clever. And over in our energy infrastructure, smart grids are using auction-based mechanisms for demand-side management. See, the grid wants to run efficiently, right? But it doesn't know exactly when you specifically need to run your dishwasher or charge your EV. By designing an action mechanism, the grid actually extracts this private consumer data through dynamic pricing. It seamlessly incentivizes your smart appliances to automatically schedule themselves only when the energy supply is optimal and cheap.
Now, in the realm of cybersecurity and defense, mechanisms are used to overcome what is known as the exit equilibrium. In these security games, some agents might just decide to opt out of defensive investments entirely, basically trying to free ride on the security paid for by everyone else in the network. A properly engineered mechanism designs specific payments and taxes to completely eliminate this exit equilibrium, ensuring that every single node is properly incentivized to contribute to the systemic defense.
So where is this all heading next? Well, the current frontier of this science is merging these somewhat static economic frameworks with the sheer predictive power of machine learning. By intersecting these two fields, engineers are developing mechanisms that can actually adapt in real time. We're talking about handling highly dynamic, unpredictable control problems in autonomous transportation and decentralized finance, continuously learning how to best align incentives on the fly. It's a total game changer. Which leaves us with this final powerful question to consider. Think about all the inefficiencies around us every day. Massive traffic jams, supply chain shortages, environmental degradation. What other broken societal systems could be fixed by simply redesigning the underlying rules? Because, as mechanism design clearly shows us, when systems fail, we don't necessarily need to engineer better humans. We just need to engineer a better mechanism.